Alright, hello and welcome. We have a bit of a potpourri of topics today, and let's just get started. So, the first thing that I want to talk about is sorting. So there was a chapter at the start of your book called Sorting that we did not talk about yet, and now it is time. Alright, so there are many, many sorting algorithms, and the book tells you exactly how to implement all of them, so I don't know the best way to go forward here. Probably won't implement much, but I'll show you examples of why you might want to choose one over the other, or why it's an important thing to learn. Alright, so here is a shuffle piece of code. This piece of code right here, it shuffles a vector, anything that has things in it that has a begin and an end. So any C++ container that has begin and end, it'll shuffle it for you. So you'll give it like a list, you'll give it like a vector, things like that. And this will make, it'll take your nice, potentially orderly array, and it'll turn it into a garbled mess, okay? It's going to shuffle everything. So just in case you ever wanted to do this to test your implementations of these sorting functions, if you decide to do that, you have to include random and algorithm, and then you have to use these magic 2 lines of code that are the C++ way of making a random number generator. And then you just call this shuffle function on your container. So it's kind of saying, please shuffle from the beginning to the end of my V. Using the random number generator, G. That's its source of randomness. Okay, so feel free to implement that. It'll be nice. And that brings us to our first sorting function, and I'm going to make sure that we're going to look at all these algorithms as well. So I'm going to bring this, zoom in a little bit. So let's get started. So bubble sort, this is the code for bubble sort, and feel free to stare at it as long as you would like. But the idea that I want to get across is bubble sort, if I can go back here, bubble sort sorts things by swapping. Bubble sort sorts an array by swapping things. It swaps things that are right next to each other. So if I had an array, I don't know, 2, 1, 3, 5, 4. The idea with bubble sort is it's going to look at the 2 pairs of things, 2 indices that are right next to each other. So it'll look at the 2 and it'll look at the 1 because those are right next to each other. And it'll notice that these are out of order, so it'll swap them. Okay? It'll swap them, and then we have 1, 2. Okay, so it'll do like, if I use a different color, now we have a 1 here and a 2 here, and it's going to continue that process. It's going to move these little arrows if I can. If I'm allowed to move them. Yes, I think. Yes. And then it'll go and look at the next 2 indices, and it'll say, oh, are those in the right spot relative to each other? 1 and 3. Are they? 2 and 3. Are those sorted? Yes, they are, so we'll move on. 3 and 5, are those sorted? Yes, we'll move on. 4 and 5, are those sorted? No, we got to swap them. 4 and 5, and I'll keep doing that. Okay? It's got to swap elements that are right next to each other. And this is where it's swapping, just on the inner side there. So it's got your, it's using J and J plus 1. So this is like J, this is J plus 1. And it's going and seeing, hey, are they in the right place relative to one another? And then this outer for loop is taking care of the worst case. So the worst number of times you'd have to ever swap is, I think, when the array is backwards, if I remember correctly. So notice that you got to move in theory, you might have to move a 5 all the way over here. And if you're only swapping things right next to one another, how many times do you have to swap this 5 to move it over? Or alternatively, how many times do you have to swap this 1 to move it over here? Well, you got to do it once to bring it there, another time, another time, another time. So in the worst case, you would have numbers that need to be moved by n minus 1 swaps in the worst case. So n minus 1 iterations of that. Okay? And so you'd have to go through the entire array again, because it might be that multiple things need to get swapped. Like this 4 also needs to move that many times. At a high level, it's n minus 1 swaps for bad numbers, and you have to, and everybody might be a bad number. So again, you're going to have to do this potentially O of n times. Okay, so the book will explain this as well, so I encourage you to read the book and see the fancy animations. But the worst case and the average case, the best case, they're all the same for bubble sort because we have to account for the worst case. It's O of n squared. Okay, and I hope that makes sense. Because you got to swap, potentially, all n numbers, they're all in the wrong place, and you got to swap them potentially n minus 1 times. Okay? So you got 2 for loops doing just that. And now, let me show you the cool part of this lecture, where I will be demonstrating with these fancy animations. So we can randomize our array, and here's a bunch of numbers. They're kind of blurry, they must be images, but we can say bubble sort, and it'll start looking at each pair. You see them in red, it's looking at each pair. It's moving them over as far as they need to go. And it's very slow, because I can't make the speed any faster than this, but it's going, looking at every pair. Hey, do they need to be moved? You can see that, oh, we're getting a lot of these ones over here. Those look like they're in the right place. It's always going to put the biggest one, eventually, at the very end, each time you see that. The biggest one is always going to be placed in the right spot after each iteration. Boop, boop. The next biggest goes into the correct spot, because that's always going to win out in the swapping game. Okay, that's bubble sort. We should say that. The biggest, or the next biggest element will always win the swapping game and be put in the correct spot. So you got to do that for all of them, and so you have to iterate just like this. Okay, so it's an O of n squared algorithm, and hopefully that's not too bad. So that's bubble sort. It's very simple. It took a while. We consider this to be slow. We consider n squared to be slow. In the world of sorting, at least. Okay? Okay, let's talk about the next one, selection sort. And before I start, I should say that I'm not really going to test you very hard on these sorting things. This is something that you'll get a lot of practice with in like an algorithms class, and this is not something that I'm going to really try and focus on in like a test. So just keep that in mind. I'm kind of giving you like the high level overview of all these things and these algorithms as well. Okay, this lecture is more for your knowledge rather than I'm going to go and test you on all this stuff on the final. Okay, it's definitely not going to be on the midterm, but maybe if anything, it's from like I'll give you multiple choice questions about this stuff from the book. I'm not going to ask you a very long question about all these sorting algorithms, all these different kinds of algorithms. Okay, so just keep that in mind, and let's move on now to selection sort. So what that does is, before I even show you these words, let me show you it happening. So watch it work, and it's trying to highlight something it highlights a small thing every time it makes its way through this array. What it's doing is it's finding the minimum value. Okay, it's finding the minimum value for the rest of the array so far, and then putting it in the proper spot. So it's like, okay, I've got so far up to here sorted. I'm going to go and look through the rest of the array to find where I need to place, or to find what I need to place into the next spot. Okay, and it's going to go and find the proper thing to put there, which is the minimum of the rest of the array. Okay? And eventually it's going to find the minimum way over here, and it's working on this part of the array only now, and voila, it's sorted. So what it's going to do, yeah, it goes and finds the minimum in the rest of the array and puts it in the correct position. So each time it's got a certain, it's got a certain portion of the array that is sorted, and then the rest is like all random order, but it's going to go and then look for the minimum here, okay, and then plop it into the next valid location that it wants to fill in. Okay, it's going to put the minimum there. So we say that it's selecting the minimum. Okay, and so if we look at the code just briefly, it's trying to fill this location I that's going to start at the first index, then move to the next one, then the next one, finding the proper thing to put there, which is going to be the smallest thing that it finds. Okay, it's going to look through the rest of the array and try and find the smallest thing there, and then swap them all. Okay, so there's a swapping that's happening. And if you look closely at all the stuff that's going on here, you got for I equals 0, I is less than number size minus 1. This is O of n times is this for loop can execute. Then you got constant work here, constant work swapping. And then in the inner for loop, again, there's constant work. And how many times does this for loop execute? Well, it starts at I plus 1, then goes to number size. So it's like the very first time when I is 0, it's going to go number size minus, or no, I think just number size minus 1 time. So let's say n minus 1 times the first time, then n minus 2 times the second time, n minus 3 times the third time, all the way down to, I guess, 1. And if you add these together, like the sum of all these, plus, 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 if you remember, like it's, I think n minus 1 times n minus 2 over 2, something like that. I may be off by a little bit, but in total, it's something involving n squared, okay? And there's n sums here. There's n elements to sum. So if you divide this by n, you get, on average, each time this for loop executes, it's going to take O of n time, on average. And so now we can multiply this times that to get the final running time of n squared. It's a bit hand-wavy. I can be more precise in office hours if you'd like, but it's O of n squared, selection sort. Okay, insertion sort is the next one, and it also keeps track of a sorted subarray, but in a different way. Let me show you. So insertion sort, voila. So it's also making sure that the first portion of its array is sorted, but it's not putting the minimum there. It's not putting the proper values there. Like, it's possible that we're going to find another minimum way down here and have to shove it way over here in the array. What it's doing is it's, okay, I'm considering the first k indices. It's making sure that everything that was originally there is sorted up to the first k indices. That's the idea. So it's going to move. It's going to look at the next thing that it needs to put in, like this small thing, and it's going to shuffle it on down until it gets to the proper spot. So the subarray is always sorted, okay? But it's sorted in a different way. It's not globally sorted. It's just like locally sorted, if that makes any sense at all. Let me say locally sorted subarray. Okay, so for example, if the insertion sort has visited up till index 5, then the first 5 elements, the original 5 elements that were there, are now in sorted order. They're not going to, insertion sort isn't bringing in like this thing over here, which eventually needs to come down here. It's going to wait. It's going to keep track of the first 5 elements, making sure that they're sorted. And then when it considers the next one, like it wants to put this one in the proper spot, then it's going to shuffle it on down to where it needs to go. Okay, at a high level, I hope that makes sense. Again, read the book. It'll be very helpful, and it has some cool animations too. So the first 5 elements of the original array are in sorted order now. And so it's just building up a sorted array still, though. Okay, it's not moving values that didn't exist in this in the range that it's considering. It's not bringing in values from over here yet. Okay, so that's insertion sort. Again, worst case n squared, because this for loop always is going to execute O of n times, where number size is n, but for once we have a while loop here, and so the idea is in the worst case it's going to have to move like the arrays backwards, and like it has to move this one all the way over here. Like it's the new minimum, right? It's the new minimum. It has to go in the front now, and so it's going to keep on moving things on average. O of n times average. Again, it might have to move this one n spots. It might have to move this one n minus 1 spots. It might have to move this one n minus 2 spots. That averages out to O of n each time this while loop is executed. So again, you can multiply these, get n squared worst case, but the best case is different from the worst case, which is not the same for bubble sort and selection sort. For insertion sort, the worst case, the best case is linear, because what if the array that you were given was sorted? It's going to try and consider each index, like consider this 52. It's going to put it in the right spot by shuffling it to the left until it's bigger. Okay? But it looks like it doesn't need to move at all because the subarray already has 51 to the left of it. I hope that makes sense. Like it's keeping track of, it only needs to go until it's bigger. Like if it was very small, it would have to move far, but because it is already large, it doesn't have to move at all. So let me click it, and bam, it's done. Linear time if it's sorted or very close to being sorted, like slightly out of order, because it's always going to just keep on swapping until, like it's going to look at the two indices, the current one and the one before it, until it's bigger, okay? Because the other one is sorted, you know that you can just put it where it needs to go if it looks like this. Here are my indices. This is my subarray, it's sorted, and if this is the next thing that I need to put in sorted order, well, it doesn't need to move at all. Okay, I hope you see that. So now, considering this one, I just look at this one, it's already bigger. I don't need to move it. If it were smaller, again, it needs to like move down. So that in words, I hope makes sense. Oh no. Well, let me get rid of those things. There we go. Okay, that's insertion sort. I encourage you to program these things. Look at the animations in the book. It's very helpful. And then now we're ready for some faster algorithms. So let's do this. The next two that I'm about to show you are called divide and conquer algorithms. And a divide and conquer algorithm, well, it's one that's recursive and the problems split evenly and don't overlap. So normally, when you do a recursive program, you might like, okay, here's my head node of my list, and then I'm going to recurse on the rest of the list. So these are kind of not very balanced sides, okay? Divide and conquer, on the other hand, the sides on which you recurse are pretty darn even. So you're able to make a recursive call on these two smaller things, and then you can make even smaller recursive calls on those. Let's see if I can move this down a little bit. Make even smaller recursive calls on those to split them up. So you divide them, and then you do the thing on each of them. You conquer them. And then you can use those results to build back up your final answer, which in our case is sorting these arrays. Okay. So you break down this problem into smaller problems until they're simple enough to be solved without any more recursion, like they're size 1 arrays. Those are already sorted. And then you build it back up using the results of these non-overlapping subproblems. And the overlapping is going to come in handy later when we talk about a different class of algorithms. So that's the idea of divide and conquer. It's just you can make recursive calls on things half your size usually. Okay, or maybe it's you can make 3 recursive calls on things 1/3 of your size, something like that. That is divide and conquer. And let's look at, because I know this is probably very vague, let's look at Quicksort, which is the first divide and conquer algorithm. So fear not these words. Quicksort, it calls a helper function called partition. So really, it comes in a pair, Quicksort and partition. And partition does the following. It picks an element. You can think of it as like the first element in the array, maybe. let's see, 5, 8, 3, 2, 6, maybe? Let's say that we pick this guy as our pivot, and then we're going to partition the array based on it. So once we pick the pivot, we partition is going to make sure that everything to the left, it's going to like split the array in two and put everything smaller than the pivot on one side and everything bigger than the pivot on the other side. Okay? So it's going to start off two indices. It's going to be like, okay, here's my I, here's my J, and I is going to be the left half of everything smaller than 5. So, oh no, 8 is bigger. I'm going to swap it with my J here. Let me use a different color. And this is what the algorithm does if you stare at it long enough. You will be programming this in an algorithms class. I promise you that. So now we have 6 and 8. We've swapped them. Again, this one's in the right spot now. We can advance J. But this one's, again, bad. So we need to swap it with our current indices. Okay, so we're going to swap the new I and J. So now we have 2 and 6. 2 is in the right spot. 6 is in the right spot. Here's the new J. And then I is either going to become J or it's going to pass it. So if they ever cross paths, then we know we're done. And we actually know because of the way we did things that J's index, I think, is going to be the one that we can always put the pivot in. So this is actually the location of the pivot, the final resting place in the sorted array. The pivot lives here. We have discovered. Okay, so that is, in a hand-wavy format, what Quicksort does. So at least the partition part of Quicksort. It's going to place the pivot in the correct spot by moving everything on either side of it. Okay, it's going to keep on swapping things while it can. So Quicksort, the algorithm now, it does the following. It partitions with respect to that some element that it chooses as the pivot. So it maybe picks the first element, picks the middle element, whatever you want. And then it puts that one element in the proper position through that. Okay? And then it has two smaller subarrays. The 5's in the right spot. So here's a smaller subarray, here's a smaller subarray. And then we can call Quicksort twice on each of them. Okay, so it's divide and conquer. We've made two smaller arrays. And it just so happens that this is n log n, and I don't have enough space here to show you why, so I'll wait till the next slide. So let me show you the good case for Quicksort. You end up partitioning cleanly. Like your pivot was the middle element, it was beautiful, and you're going to make recursive calls on these smaller subarrays to go off and partition them, hopefully with the elements that are the pivots in the middle, then go off and partition those until you get down to size 1 arrays, which are already sorted. Okay, and then you build back up the answer. So at any given moment, you'll have made a certain number of recursive calls, and if you always split in half, you'll be using log base 2 of n space, because there are log base 2 of n calls in the best case. And each call just requires constant space. You're not you're editing the array in place. And the reason it's n log n in the average case is that well, you're making log of n calls, and then also you are building up these answers in the following way. You are swapping potentially n elements in this call. You're swapping n over 2 elements in this call. Then you're swapping ... n over 2 to the I something, 2 to the k, whatever you want to use as an exponent. And all of these things added together are n total. Okay? So it's like n plus n over 2, n, n, n. So at each level you have n things, and it's log n times. Okay, so that's the idea. N log n time log n space in the best case. In the worst case, you have a horrible pivot. Okay, in that case, you're splitting unevenly. Okay, you'll split, and it's like, oh, okay, here's this one partition, and oh shoot, I need to go down and sort this other array. So you got like size 1 and size the rest. And again, size 1, size the rest. And you can see how this would require height order n. So not only are you going to use order of n space, and I guess these are capital N's, that's going to be n squared time, because at each level you're working on n elements, trying to sort them. Okay, you're partitioning, swapping things. Okay, and you're doing that at n levels. Oh man, does that suck. So that is Quicksort's space and time complexity. And now let me show you some pretty animations to make sure it's working. So if I randomize this array and I click Quicksort, the way this animation works is it's going to show you the pivot with a horizontal line. It'll make the decision like, okay, that's my pivot. Everything above it's going to go on the right side. Everything below it's going to go on the left. So it made a horrible decision for the pivot right now. And now it's going to recursively sort the subarray. And here's a nice pivot. Here's a nice pivot. Everything to the left is smaller. It's going to recurse down. Recurse. Go back up. So it's swapping everything. So it's pick the pivot, swapping things, making sure that everything is smaller is on the left, everything's bigger on the right, and it's building up the resulting subarrays. And oh man, was that fast. Okay, so that is Quicksort. And also in your book, you have a cute little animation as well. So we're going to be the partitioning. So our pivot value is pretty horrible right now. It's 72. So let's find everything that's smaller than 72. Boop, boop, boop. Partition. So now we're working on this subarray down here. Can I do that? Yeah. Okay. New pivot value 68. Everything's smaller than that. It's again a horrible pivot. Partition. New pivot values 37. Okay, that's a better one. Everything's smaller. Or those. We're gonna pivot values 3. There's nothing smaller. So that's sorted. That's sorted. 37, 55. Pivot values 37. Beautiful. Sorted. So we've sorted this much of the array so far. And then we're working on the right half now. Pivot value 72, or they're both 72. Sorted. Beautiful. And so we've sorted the entire array by just swapping things around with respect to a pivot. Okay, so that is Quicksort for you. And it is fun to implement. The one I will implement for you is merge sort. That one's exciting. So what merge sort does is, well, it has merge in the name. It's going to call a helper function called merge. It's again a two-step process. You're going to recursively sort smaller subarrays, and you're going to build them back up. So for example, if this is our array, 8, 6, 7, 5, 3, 9, you're going to recursively sort half of that. Well, that's a 3. Here's my half. I'm going to recursively sort this one into 8. Recursively sort. And recursively sort. And this one's going to become 6, 7, 8. And this one's going to become, we get to assume this by the magic of recursion, 0, 3, 5, 9. And then, after we've recursively sorted, we will merge them back. Okay, and so you'll be like, okay, consider these two indices. Which one needs to go first? Well, it's the 0. And in fact, let me do it opposite. Like merge back. So you kind of take two indices, like here's your I, here's your J, and you need a the space complexity is not as good as Quicksort in the average case because you need a temporary array. So it's going to be O of n space, unfortunately. 8, 6, 7, 5, 3, 0, 9. So you're going to look at I, look at J, and then be like, okay, which one's... Oh, sorry. Wrong end for J. You're going to start on the left half. There's your J. So now you look and see, okay, which one's smaller? The thing at the I or the thing at the J? Oh, we're looking at J. So we bring in the 0. That's the next... Now this is sorted. Increment that one. Okay, so now we're looking at 3 and 6. Which one's smaller? 3. This is the merge procedure. Okay, 3 is good. 5 and 6. Oh, 5. Okay. Now we have 6 and 9. We'll take the 6. Why not? 7 and 9. Take the 7. Oops. 8 and 9. Take the 8. And now that we're done with this one, we can just take the rest of the other. So now we include the 9. And that's your merge function. Beautiful, huh? So the reason you need a separate array and your complexity for space is not as good is because of the following. You might think you can merge in place, but that is not the case. So let me give you an example with the arrays, subarrays 1, 5, and 2, 3. So let's pretend we were trying to merge these two back in place. So what you would want to have done was, okay, here's my I, here's my J. I is good. J is smaller, so this is now my I, my new I. Consider 5 and 2, which one's smaller? It's J, so if I'm not going to use another array, I have to swap these. So this becomes 2, this becomes 5, and now suddenly I think that I'm done, but really this one's out of order. So unfortunately, it doesn't work in place without some fancier tricks. So you have to use a separate backup array for a second, and that kind of kills your space complexity. So that's the reason. You would end up with, you thought you had a sorted array. That's how this merge algorithm works. It assumes that both sides are sorted arrays, but when you swap things, you might end up with an unsorted array. That's no fun. So now let's talk about space and time complexity. And this one's quite a bit easier to talk about, and then I'll go and implement it for you. So boop. Here is my original array, and I'm going to cut it in half, remember. So eventually, I'm going to cut it in half, as many times as I can until I get down to easy cases to sort. And what is an easy case for sorting? It's a single element array. Okay? So maybe these are size 2 each or something. Boop, boop. Boop, boop. Boop, boop. Boop, boop. Okay, so it cuts in half everything. So it's log of n levels, on the order of log of n levels. And how much work is it doing at each level? Well, it's the merge operation. So we got to merge, well, at this level there's nothing to do. At this level we have to merge things. We have to merge these two subarrays back up. Actually, I have to do that for all of these. Merge them back up, merge them back up, merge them back up. You get the idea. How much effort does it take to merge? Well, like I was showing you, you're just keeping track of pointers, and you're going through each subarray. So it's going to be linear in the size of that subarray. So it's going to be, at each level, you're working on O of n things, or you're working on n things exactly. So n things to merge at each level, except for the last. Technically not that one. Oh well. So that's why you just multiply n now by log n. You got it. So that's why it's n log n. And this is the worst case as well as the best case. The best case is the worst case. You make sure you split down the middle. And it's O of n space because you need to save a copy of a subarray. And the size of the temporary array that you might need to make is size n. Okay? So that's the idea for merge sort, and now I'm going to go and implement it for you. So there's two functions, merge and merge sort, and let me show you merge sort just quickly. Boop. Sort the left half, smaller halves, merging up all this left side. Bam, this one's sorted. Now it's working on the right side. Bam, it's about to be sorted. And now they're merging the last ones. And you can see at the bottom as well what it was working on. So here's its subarray, it's its temporary array. Bam, bam, Bam. So it's beautiful. It's fast. It's n log n. In practice, even though Quicksort has a bad time complexity, in bad cases, Quicksort is slightly faster. The constant factor, in the best case, is a bit faster. And there's no copying anything. You just work on the same array. It's in place. Okay, so that's merge sort. In words, let's go to code now. Boop. That was probably from office hours. Okay, so merge sort.cpp. So I'm going to make my favorite array in main. All right, let's make a vector array now. Phi equals 8675309, and we're going to merge sort this vector. So merge sort is going to take reference to a vector, and then we also have a merge function that merges things back. Dun dun dun. And there's some extra parameters that I have not included yet. So let's talk about those. In order to say, like in order to work on some portion of the array, you have to give indices of the starting and ending indices. Okay, so to know that I want to call merge sort and work on this small subarray, I need to give the starting index and the ending index. Like same for this one. So start and end, inclusive. And then we'll also figure out what merge needs as well. So, boop. Merge sort, here's what you do. So, sort half the array in the recursive case. Sort each half. The array, and in the base case, the array is size 1. So, or 0, I guess. So it's already sorted. So if start minus n, how many things that I need to, oh sorry, n minus start, these are indices. How many things do I need to sort? Well, if start is equal to end, or they're different, like if it's less than or equal to 0, then we're going to just return. There's no sorting necessary. Otherwise, we're going to recursively sort. So I'm going to sort this vector from 0 to v.size minus 1. Okay, hopefully that makes sense. And then in the recursive case, we're going to sort each half and merge them back. So we need to merge sort half the array. So int mid equals start plus end divided by 2. We're going to merge sort the two halves, v start mid, that's the first one, and then merge sort v mid plus 1, end is the second half to sort, and then we're going to merge them back. So v, we also need to know where the midpoint is, so start, mid, end. Okay, so those are the 4 parameters to this. And we need mid in the middle. So merge the two sorted subarrays. Start mid and mid plus 1 to end. Okay, those are the two indices of those arrays that we want to merge together now. And hopefully the recursive case makes a lot of sense. It's like, all right, recursively sort the smaller arrays. And then bring them back together. Build up the bigger sorted array. And so now we just need to worry about merge. We need to merge things back. So again, if I go back to this example, I have these indices. I have these two places that I want to start. I'm going to put my I right here, put my j right here, and just move on down and fill them in a temporary array for a second. Okay? So start on the left and start on the left side of each set of array. So int I equals start, int j equals mid plus 1, and then we're going to keep on moving them. So figure out until, just keep going. So while I is less than j, while their paths haven't crossed. No, sorry. That is incorrect. There is a while loop, but that was the wrong condition. I was thinking about a different kind of sorting. All right, so while something, we need to move things around. Okay? So I is going to start here, j is going to start here, and we want to keep on moving through these arrays just like that. Okay? So we know that I is done when it hits like j plus 1, or sorry, when it hits, mid plus 1, and then we know that j is done when it tries to get past the end of the array. So while I is less than or equal to mid, and j is less than or equal to end, I think we're good. We're going to keep on moving. Dun dun dun. So pick the smaller one. We have to choose for ourselves v at I and v at j. So choose the smaller one and put it in a temporary array. So vector int temp of size, how big? End minus start plus 1, I think, right? And, okay, so we're trying to put it at index 0. So int next index in temp array equals 0. So we're starting out with the first index to fill in. So pick the smaller one. If v at I is less than v at j, then we're going to put v at I in the next index. So temp at next index in temp array equals v at I, and then increment I. Otherwise, vj was bigger, so we're going to do that one. So instead of I, we're going to say j. Increment j. Okay? And then in either case, we have another index to search through and find the next thing to put in. So index, we're going to work on the next index, filling that in now. Ready to fill in the next index of the temporary array. Okay, so we've got all this, and eventually this will stop. So once the loop stops, we've run out of one of the arrays, one of the subarrays. So either like we moved I all the way to here, or we moved j all the way to here, and in which case we need to take the rest of the other one. Okay. So if it was the case that I is now greater than mid, take the rest of the j's. Else, take the rest of the i's. Okay? In either case, just, okay, we got through this much and this much, just take the rest of this subarray over here, because maybe everything was bigger. Okay? So how do you take the rest of the j's? That involves saying something like if, or no, this is a loop, for int, I already know. Let's just use while because I've already included j as a variable. So while j is less than or equal to end, just fill it in like we were doing. Take the j's, index the array at the next location. Okay. And the other one is the exact opposite with i's instead. Okay. Unless I've made a horrible mistake, and I probably have, this should do the trick. Oh, sorry. No, the one horrible mistake that I know I've made is I haven't copied the temp array back into the actual vector. Silly me. So we made our temp array, and now we got to put everything back in the original one in order. We just got to copy it all over. So for int, I can reuse I now. I equals start, I is less than or equal to end, I plus plus. And then I also need some another index, like int idx equals 0. This will be for the temp array, idx. I can say v at I equals temp at idx, idx plus plus, I plus plus, all should be well. Okay, so let's try this. And if I edit this video, that means that I did it wrong, and you can laugh at me. But this is morally correct, if not completely correct. I have something out of range. Oh no. So I'll go and fix that, and I'll be right back. Ah, silly me. So I copied this and didn't look at it. It's got to be while I is less than or equal to mid, of course, because that's where the smaller subarray ends, is mid, not end. Silly me. So that was my fault. And now it works. Dot slash merge sort. Bam, do we have a sorted vector. Isn't that cool? And we did it in n log n time, so that's like linearithmic is the name for that. And with that, I think that is all the time I have for you in this lecture. I will come back with some more in the next. One more sorting algorithm and then some other algorithms as well.